Good afternoon, this is Schweitzer, and part of our review series for the AP exam, we have this particular um, review session is on ice table mathematics. Guaranteed to be around at some point, somewhere. Um, Now, salt equilibrium can take many shapes or many forms on the AP test, and solubility is one common method the AP uses to test equilibrium. Expect this type of question. Silver sulfate is added to 500 milliliters of water at 298. The mixture is stirred after a period of time remains and solids on the bottom. Write out the equilibrium reaction and the KSP. All right, so just to review, when we're writing out, again, you should be trying all this stuff before I do it. Doesn't do much good to watch me do it, but all right, so first things first, silver sulfate is the solid. Doesn't have us draw a picture, I don't believe, here, so if I were to draw a picture of this, it would just be a beaker. I'd have some water. Whenever I dissolve the silver sulfate, it's Ag2SO4, and I'd have Ag pluses in here, Ag plus and SO4 minus 2, solid on the bottom. And the reaction or equilibrium expression, reaction to KSP, we always start with our solid on the left. That's how KSP works. So it's Ag2SO4 and going to and from Ag plus and SO4 minus 2. And the 2 goes there. All right, so my KSP expression is KSP equals concentration of products over reactants. So it's the concentration of Ag plus squared, concentration of SO4 minus 2. Don't forget your charges on these guys. They'll mark that wrong. Good enough there. And it is in fact a solid. So turn the concentration of each ion in the solution. Okay. So we have a saturated solution. So you have to have the solid here in order to have the back and forth stalemate taking place here. That's what this area was here. No solid, well then there's no back and forth stalemate. So in this case, pretty standard calculation. I could initial stoichiometric ratio n, kind of try to weave that in there. This guy is not playing a role. I have none of this present in solution before I start. I'll be gaining x of this, I'm gaining 2x of this, gaining x of this. So those are always in 2-to-1 ratios because there's nothing there to start with. Just 2x and x. Plug these values into the expression, and it's going to be 1.0 e to the negative fifth equals 2x squared times x. That gives us 4x cubed equals the KSP of 1.0 e to the negative fifth. So to get this thing here, we're going to divide out the 4. So 1.0 e to the negative fifth divided by 4, and then cube root this thing or raise it to a power of 1/3. So caret parentheses 1 divided by 3 gives me 1/3, and I get 0.0135. So x in this case will equal 0.0135 moles per liter. All right, student hypothesis. A 1 liter solution has the ability to dissolve more silver sulfate, and this will result in higher solubility. Justify or nullify? The answer is nullify. Okay. There is a true statement here. You will be able to dissolve more ions, but your ratio of solute okay, to solvent, all right, is the same. That's not changing. Only way to really change this ratio is to alter the temperature. All right, student hypothesis. 500 milliliter sample solution of 1 molar silver sulfate, or sodium sulfate, has a lower solubility of silver sulfate than distilled water. All right, so what this thing is saying here is that if I have a beaker, all right, and I'm going to try and dissolve silver ions, I'm going to try and dissolve silver sulfate, just like in the top one. I'm going to attempt to put this stuff in 2 beakers, this one or the other one. Okay, the bottom one, or the one on the right, only has water, nothing else in there. This one's got stuff in it. Na plus ions. It also has some sulfate ions. And it's saying that the solubility of this silver sulfate, should probably clarify that some way here, is lower. So, 500 ml solution of sodium sulfate has a lower solubility of silver sulfate than distilled water. And this is true. Obviously, there's a right. Now, the sodium doesn't matter, but because there's some sulfate in here, that would be a common ion. And therefore, there's only so much room to dissolve stuff. And if there's already some stuff there, then, well, then there will be less. Okay. Calculate the solubility of silver sulfate in this mentioned solution. Okay, so let's do this. The way this works is like this. Ice table mathematics. Ag2SO4 to and from Ag plus SO4 minus 2. Initial stoichiometric ratio end. Solid is not playing a role. Now before, up here, we had 0 here. That means there's nothing in the beaker to start with, like this one. So X ends up being 0.0135. But if we have something in there already, then our concentration X should be smaller. So this guy here would be 0 because there's no silver in the solution, but there is some sulfate. The sulfate is 0.1. I'll be then dissolving some silver sulfate to get gaining 2x, and I'll be gaining x here. All right, this is 2x plus x, 0.1 plus x plus 0.1 plus x. All right, so what do we got here? Plug all these guys in, and they want to do it right here. Okay, so let's do it. 1.0 e to the negative 5th equals 2x squared. And now here's where I'm going to use my shortcut rule. 0.1 plus x. X is very small because of the k value. Therefore, 0.1 is what we'll go with. This is 0.1 and to the first. All right, so you can put all this together however you want, but solving for x. All right, I go 1.0 e to the negative 5th divided by 0.1, and then divided by 4, and square root. The previous answer is 0.005. All right, so x equals 0.005 moles per liter, less than that one. So my answer here was correct. Okay, it is less. Now again, just a quick reminder, I divided out this guy, and then this little chunk here became 4x squared. So I divide the 4 out and square root it. All right, next problem. We have 50 milliliters of 0.1 molar Na2SO4 is mixed with 50 milliliters of 0.5 molar HNO3. Will a precipitate occur? All right. So now we know that from our expression that the K value equals concentration of Ag plus times the concentration of SO4 minus 2, and this one is squared. That the combination of these two ions together cannot exceed the K value, which is equal to 1.0 e to the negative fifth. Again, that's important to understand that I can have lots of silver and a little bit of sulfate or vice versa, but I can have lots of both of them. And together, this algorithm cannot exceed that, or I'm holding too much and I would have a solid produced. Okay, so what is this? Now, if we're at equilibrium, we call K is 1.0 e to the fifth, but if we're not at equilibrium, we call it Q. We've had lots of time to do some Q stuff, but all right, let's plug in our current concentration. So what is the silver ion concentration? All right, now they're going to want to see some work on this, but in this case, we're doubling our volume, and silver is only present in this guy. So the 0.05 is going to get cut down to 0.025 moles per liter. You can't just make that. You need to just either use the dilution formula, which is M1V1 equals M2V2, or you need to make some statement about that your moles are staying the same or doubling our volume, so our concentration just gets cut in half. You'll have a standard point for that. All right, so, and they're not always going to do 50 and 50. So if you're doing 50 and 75, well then, yeah, I would use this, put this at 50, and this at whatever my new volume happens to be, and solve out for M2. All right, so this now is 0.025, and it's going to get plugged into the expression and squared. The other guy is 0.1, and there's one of them. Okay, so the doubling would be 0.05, and then here we go. So we have 0.025 squared equals times 0.05 equals 0.00040 zeros and the 312. So now that means this guy is equaling 0.0000312. That's equivalent to 3.12 e to the 1, 2, 3, 4, 5 e to the negative fifth. That's my Q value. So they'll have 1 point for getting your concentrations, 1 point for generating your Q, and 1 point for making a Q to K analysis and giving an answer. In this case, Q is bigger than my K, and because K is proportional to solubility, larger K's mean more soluble. So we're too big, so we need to get smaller. So that means we need to dissolve less. So precipitation has to occur. So yes, precipitation is going to occur. But otherwise, Q is a ratio of product over reactants. And so my Q is bigger than my K, so Q has to get smaller. Product over reactants. I will be driving to get smaller towards reactants, which means I'll be driving to the left, and that means there are other reactions above here, and it's right there. I'll be going this way, which means more solid formed. However you want to do it, just don't memorize anything. We'll be able to work it out. Okay, ethanoic acid. Vinegar, there it is, establishes an equilibrium very quickly upon dissolving in water. Write the hydrolysis reaction for vinegar. Okay, so C3H, not vinegar, CH3, COOH, and you want to be aware that this is the H that's donated, plus H2O yields, all right, makes H3O plus CH3 COO negative. I think that's right. Acetic acid could also be seen as being HC2H3O2. All right, that's the H that's donated. That's it. All right, so it says for a given temperature, a 0.5 solution creates a pH of 3.6. Determine the concentration of each species under equilibrium. Okay, so each species is going to be the all right, so this guy is, okay, so first things first, this represents the H plus ions. Let's do that one here. 10 to the negative 3.6, and that will give us the concentration of the H plus ions. Second log, negative 3.6 is 2.5 e to the negative fourth. So 2.5 e to the negative fourth. So this concentration will equal this guy and that guy, the H plus. Because if every time you get one of these, we also get one of these. Water doesn't have a concentration, and this guy is going to be the original concentration of 0.05 minus the 0.0002425, which basically is 0.05. So, long story short, what I did here was that basically, if I'm going to represent HX as my acid, plus H2O yields H3O plus X negative. X negative is going to be this guy right here. This initial stoic ratio, and this guy is 0.5, not playing a role as a liquid. 0, 0. I'll be gaining 2.5 e to the negative fourth. And that's the same for both of these. Alright, so this guy is just going to be minus 2.5 e to the negative fourth. You'll note when you subtract that, you get 0.499999. So our shortcut method just says that this is essentially 0.5 or 0.4999. All right, determine the Ka. Remember, anytime you want to determine the Ka, you fill the ice table out, and everything at the end just gets plugged into the expression. So it's going to be, the expression is right here. So it's going to be the Ka equals the concentration of H plus ions times the concentration of X negative ions over the concentration of HX. All right, and this math ends up being very similar all the time. So 2.5 e to the negative fourth. I'm going to square this thing to show there's two of them. And then divide by 0.5 equals. So square the top one divided by 0.5, and I get 1.26 e to the negative 7. So 1.26 e to the negative 7th. And that's my Ka value. That's my Ka value. All right. Just some pure basics here, stuff we want to do. One of the two chemicals listed below are acidic. Which one and why? All right, well, this guy right here is an alcohol. This one is not acidic. And this one is an organic acid called methanoic acid. It is acidic. And the reason why is that bond is weakened. And why is it weakened? Because of the fact that this oxygen and this oxygen are drawing electrons away from that bond, causing it to be weaker. And this guy is lost, producing an H plus ion. All right, next. A standard copper zinc battery is used in most electronics via the following reaction. Again, copper zinc batteries, pretty common. This is the alkaline battery, typical AAA, AA battery. They are becoming less common nowadays as lithium sort of takes control. The reaction has a standard voltage of 1.1 volts. Tracking this reaction at STP, create a graph on the chart provided showing relative concentrations as the reaction is equilibrium established. Okay, a couple things I'll mention about this is one, we have an electrical potential that is equaling a positive 1.1 volts. Okay, that can be made proportionalized to a negative delta G, which means we are traveling in this direction. We're consuming these guys, producing these. Now, solids, they don't have a changing concentration. So this concentration is going down, this concentration is going up. If we're starting STP, and they're both at 1 molar, and the zinc would just be dropping to a certain level, assuming that, let's say, established right here, this guy would just be mirroring that like that as well. Equilibrium established at this point here. All right, determine the equilibrium constant for this reaction. Okay, so they have a couple different reactions. They're on your laminated sheet. In this case, we have a few different ones. Let's just jot these down. Delta G is equal to negative RT natural log of K. We have another one which is delta G is equal to negative N Faraday's constant times the standard electrical potential. So what they want you to do here, and this is to use two equations. We have this, flip to delta G, and then use delta G here to find K. So this is really just a plug and chug problem, but I would point out more importantly, this guy is positive, so this should be negative. This is negative, therefore this should be, K should be greater than 1, because these are primes. Okay, so a couple things we want to point out here. I'm assuming by the time you have listened to this, you know all the electrochemistry. Okay, so let's plug this in here. We got 1.1 Faraday's constant. Okay, that's the charge on 1 mole of electrons is 96,500 on your laminated sheet. N is the number of electrons exchanged in the reaction, in the balanced reaction. We have +2 and -2, so the number of electrons, 2 are lost, 2 are gained, and it is -2. And there we go. All right. Let's do our math here. -2, all right. -2 times 96,500 times 1.1 equals, all right, -212,300. All right, so key idea here is -212. All right, sig fig wise, Well, I'm going to just wait till the very end to adjust my sig figs. That's a big number here. This is a key point here. This is in joules. All right, now it'll matter for the next one. So the next guy, I'm going to plug into this guy. So I'm going to put in the negative 212,300. All right, equals negative R. Now R, because I'm in joules, is 8.31. And then times 298 times the natural log of K. So multiply, divide out, and then inverse log, natural log that thing. K equals. All right, so I'm going to divide by negative 8.31, divide by 298. I get 85. So I'm going to get, in this case, this is 80. This is 85. So I'm going to inverse natural log this thing is going to, my K is going to equal to e to the power of 85. So it gets a little bit bigger. Second natural log, previous answer, I get 1.7 e to the 37th. Holding sig figs 1.7070 e to the 37th. Obviously, this is a positive value. That's the answer. All substances start at 1 molar. Can you calculate the concentration of each substance at equilibrium? All right, so in this case, we do know that the concentration of zinc goes down and this goes up. So in this case, the chemical reaction is going to be K equals the concentration of the copper ion, and this is the concentration of the zinc, 2 plus, equals my K value. So it would be the, I'm going to be, let's write out the whole equation, get some room here. So this, I'm just going to write the zinc side here. Zinc 2 plus goes to copper plus 2, initial stoichiometric ratio end, and it's going to be 1 is my initial concentrations, minus x plus x. And then this is going to be 1 minus x and 1 plus x. All right, so my K value is 1.70 E. It's awful sloppy there, sloppier than normal. 1.7 e to the 37th equals 1 plus x over 1 minus x. Yeah. All right, so essentially though, now we can solve this out. All you gotta do is plug this guy over here, distribute, and then get all your x's on one side, all your non-x's the other. But this thing is got a very large K value. So essentially, this almost all of this thing flips to here. So I'm going to say that this thing, the K value, x is going to be very close to 1. And the answer is that essentially the zinc, this will be the copper, and the zinc actually, let's make them all really close to 0. So the zinc is going to be 2 plus ions or very close to 0 concentration. And this guy is very close to 2 molar doubles. Okay. But the math actually should be very close to 2. We'll move it on from there. All right, so next up here we have a 0.5 molar solution of sulfur dioxide gas is introduced into a 2-liter vessel containing 1 mole of oxygen and allowed to react. All right, at equilibrium, the concentration of SO2 was equal to 2.5. Very standard got a little room here to do ice table. The SO2 is 0.5 moles in a 2-liter vessel. I like doing my equilibrium in moles per liter. So 0.5 divided by 2. Okay. That's what, 0.25. And 1 mole of oxygen. 1 divided by 2 is 0.5. And we don't have any of this. I will be losing 2x here, losing x, and gaining 2x. All right, and this is difficult to do unless, of course, we have this. So S equals 2.5. All right, solve it out. That means x equals 1.25. All right, so to get 2.5 mole, I want to make sure, all right, 0.5, so we have 0.5 divided by 2 equals 0.25, and the 0.5 divided by 2 equals 1. Yeah, 1 divided by 2 is 2. So my concentrations are right. Here's the issue. If x is 2.5, then in this situation, I get more than I had to begin with. So let's change this now. I'll likely change this as you see it. So let's change this to 0.25, and I will make that change. 0.25 molar. All right, so that means that this is now 0.25, which that means my x value is half of that, which is 0.125. Okay, maybe that's what I intended. All right, so this is going to be x is this is 0.125, and this is the same thing, which is 0.25. And that even comes out to 0. Even that gives me 0. So we wouldn't be in equilibrium at that point. Okay, so let's change this again. The reason we wouldn't be in equilibrium because you can't have anything run out. So let's say it's 0.2 molar. All right, I like that number better anyways. Let's erase some of this just to give us a fresh start. All right, good enough. All right, so I'm going to lose x, lose 2x, lose x, gain 2x. This is 0.2, and therefore x equals 0.1. I will therefore be losing 0.1 and down to 0.4. Losing 0.2 down to 0.05. All right. What's the equal to expression? Anytime you want a k value, plug it into the expression. The expression is products over reactants. So it's going to be 0.2 squared over 0.05 squared times 0.4. Do the math. All right. And we did B already. We're doing C now apparently. 0.2 squared equals divided by 0.05 squared divided by 0.4. And we're showing a value of 40. All right. This reaction is running at the specified temperature. Doesn't have to be exothermic or endothermic to run. Okay, so we're jumping all around here. Keep in mind, delta G is equal to delta H minus temperature times delta S. All right, and we just got done with this a little bit. We know delta G is negative because it's running. What is this guy here? You'll note that in our reaction that we have essentially, what are we doing for entropy here? Looks to me like we have not a whole lot of change in entropy. We got solid to solid, aqueous, aqueous, all the same numbers. So this thing here likely, in this situation, this is kind of probably a moot point. Not a whole lot's happening here. So I'm going to say that this guy likely will be negative. So I would say yes, exothermic. Does it have to be exothermic to run? I think so. This is not enough of a driving component to drive this reaction. Essentially, it's very close to zero. So this needs to be negative. All right, on to our last question here. Calcium, also called slacked lime, in industry is used frequently through the food industry. It is non-toxic and mildly basic. All right. Equation. Write the equation responsible for the basic properties of calcium hydroxide. So basic. So it's going to be calcium hydroxide yields calcium 2 plus 2 OH negative. All right. Determine the pH of the solution. Now again, this is a situation where the hydroxide is producing the basicness, but it's based on solubility of the calcium hydroxide. So initial stoichiometric ratio N not playing a role. We have 0 to begin with, and we're just going to be gaining towards equilibrium. X of this and 2x of that, x and 2x. All right, 5.5 e to the negative 6th equals products over reactants, so it's going to be x times 2x squared, 2x squared. Now hopefully you see why I did that. That's the equilibrium expression. All right, that's going to equal 4x cubed. I'll divide the 4 out and cube root it. 5.5 e to the negative 6th divided by 4 and raised to the power of 1/3, and I get 0.011. Alright, so in this case, x equals 0.0111, 0.0111. And of course, to get that into pH is negative log of that value. We'll give you my pH. Well, I give my pOH. Negative log of that previous answer is 1.95. 14 minus that is 12.0. So in this case, it's going to give me my pOH. 14 minus that is my pH, which is 12.0. And no discussion of equilibrium would be appropriate without that of Chatelet's principle. Which of the following would reduce the solubility of slacked lime? So we want to know which stuff could drive it that way. All right, adding additional water, okay, reduce the solubility. Solubility would be the maximum amount that can dissolve. So per solvent, adding additional water would allow more to dissolve. It's not going to make it more soluble. Adding a catalyst, I guess. No. This is going to just allow us to go from here to here faster to get to the current solubility state. Faster will not allow it, like stirring perhaps, would not allow us to get more dissolved. Adding NaOH, this would be would actually reduce the solubility, driving it this way. So this is a yes. Adding an acid would actually remove that item, driving the reaction this way, and that would increase the amount that would dissolve. So that would be a no. All right. That is where I believe we'll be stopping. Thank you very much.